Welcome to the online platform of KTCD College of Arts and Science. I am RESHMISREE, HoD Department of Mathematics. Important property of real number is the set of real numbers is uncountable, and the real number, we can say the real number is has infinite many elements, a large type of infinity. Okay, so the set of real numbers is uncountable. The set of real numbers R is uncountable. We will prove this by contradiction. What is uncountable means? Uncountable means countable means there exists a function, one function and onto function. Uncountable means there does not exist such an one function and onto function. Okay, then we will prove R is uncountable by contradiction, that there exists a one and onto function f from n to r. We are assuming that there exists an unknown function and onto function f from the natural numbers to the set of real numbers. Hence we can enumerate the elements of R. Okay, hence we can enumerate the elements of R. If we let the first element in the natural number is 1, isn't it? Second element is 2, third element is 3, etc. So 1 has an image, that is f of 1. We take that f of 1 as x1. So we let x1 equal to f of 1, okay, and x2 equal to f of 2, the image of 2, and x3 equal to f of 3, the image of 3. We can continue like this. We are assuming that the function is 1 and onto. Then from our assumption, f is onto means that, what is the definition of onto? Definition of onto says that there exists a range is f of n. Okay, so f of n equal to r. So we can write from the onto assumption, we can write r is equal to x1, x2, etc. That is taken as equation number 1. So that every real number appears somewhere on the list by assumption. Since f is onto, every real number appears somewhere on this list. Okay. Now our aim is to prove this as a contradiction. On and onto is a contradiction. So we are going to produce a real number that is not in this set. We are going to produce a real number that is not in this R by using the nested interval property. Okay. So nested interval property, there will be a sequence of nested intervals, and the intersection of these intervals has at least one element. Okay, the intersection is non-empty. So let I1 be a closed interval that does not contain psi x1. We are assuming that I1 is a closed interval. This will be I1, and it does not contain x1. It means x1 is out of this set, here or here. Okay, here or here. Let I1 be a closed interval that does not contain x1. Next we assume that I2 is another closed interval which is contained in I1. Here is I2. Okay, I2 is contained in I1, which does not contain x2. So x2 will be here or here. I2 is contained in I1 and x2 is not in I2. First we take that I1 is a closed interval and that does not contain x1. Okay. Hence I1 contains two smaller disjoint closed intervals. We can find two smaller disjoint closed intervals in I1 and that x2 can only be in one of these. In x2 can in this set x2 can only be in one of these closed intervals. Okay, so we are assuming that I1 be a closed interval that does not contain x1 and I2 be a closed interval contained in I2 that does not contain x2, and so I1 contains two smaller disjoint closed intervals and x2 can only in one of these two disjoint closed intervals. Okay. In general, given an interval in, construct in plus 1 to satisfy this method. In plus 1 is contained in in and xn plus 1 not in in plus 1. Okay. In contained in in plus 1 that does not contain the element xn plus 1. We now consider the intersection. Intersection n is equal to 1 to infinity in. Okay. If x0 is some real number from the list in equation 1, then we have xn0 does not belongs to in0. Here we take if in plus 1 contained in in plus 1, then xn plus 1, this suffix element does not belongs to in plus 1. Hence if xn0 is a real number, then xn0 does not belongs to in0. So it follows that xn0 does not belongs to the intersection of in from n is equal to 1 to infinity. Hence the intersection will be null set. But we are given the nested sequence of intervals, but we are assuming that the list of in equation 1 contains every real number, and this leads to a contradiction that intersection equal to null set. However, the nested interval property asserts that intersection is not equal to null set. Therefore, by nested interval property, there is at least one x in this intersection. N is equal to 1 to infinity in that cannot be in the list R. So, that cannot be in the list R. R is equal to x1, x2, etc. xn. We can find another real number x which does not belongs to this set. This is a contradiction to our assumption that we can enumerate the elements of R. Hence, we cannot enumerate the elements of R. R is uncountable. So we can write R is uncountable set. The cardinality of R, informally speaking, a large type of infinity. R has infinite elements. R has a large type of infinity is the cardinality of R speaks. R is uncountable means R is a type of large type of infinite set. A finite set that is not countable is called, an infinite set that is not countable is called uncountable set. R is an infinite set that is not countable. We are already proven. So that set is called an uncountable set. Hence R is an uncountable set.